Okay, so this is one possibility, okay? And that just means you divide the first row of your original matrix by whatever your first asterisk is, assuming it's not 0. If it is, well, we worry about that, we patch that up, okay? So we're not going to worry about every possibility yet, but you get the general idea. You divide this thing to get a 1 here, and then you have whatever multiple of that it takes to get this, which would be negative whatever this is times the first row added to the second, and you get this, right? And then, since you get a 1 here, presumably, you're going to get a 0 here, right? And that completes it. Simple enough. Okay? Here, you divide the first row by whatever the first asterisk is, and you get this. And then add whatever multiple takes care of the first number here. It takes care of them all. Meaning that the second row was a multiple of the first in the first place. Okay? Simple enough. Now, what's this mean geometrically? This means that what you get, and of course you're going to want to try to prove this, but I think, first thing I'll ask you to do is give me an example of everything. A representative example, no special numbers there, okay? And then tell me why it always has to do that. That's the proof. Example. Understand what it's saying completely. See how it looks when you write out all the equations and stuff. Okay? And then see how it's going to look in general. That's a good way to approach proof. Get an example to make sure you understand the phenomenon, then see if it'll generalize. Okay? Okay, so anyhow, if you get this, well, it's going to tell you that the domain's R3, the range is all of R2. Okay? What's this tell you? Well, the domain is R3 because any matrix like this will multiply any vector in R3, right? You multiply any vector in R3, your domain is R3. The range is what you get, and the range here is what? First of all, where does the range live? Well, it lives in R2, because anytime you multiply this vector by a vector in R3, you get a vector in R2, right? So it's something in R2. What is it?
Would it be R1?
Well, not necessarily R1, but it's going to be a line, which could be identified with R1, but it's a very specific line within R2. It's not just any old R1 and R2, right? Not any old subset of R2 constitutes a straight line. Got to at least be through the origin, and it's still got a direction.
So
okay.
A R1 in R2.
No, you wouldn't say that.
There's probably a better
You
way
wouldn't
of putting
say
that.
You would say this. But your intuition is right, but you wouldn't call it R1, because R1 is not specific enough. Okay? So the range is a line in R2, i.e. a one-dimensional subspace of R2. Okay? Represented by a line through the origin. Okay? in a specific direction. So it's going to look like the picture we have for that first transformation we looked at. That line parallel to 1, -2. Okay? Make sense? Now, in general, if you have higher dimensional spaces, well, you could have Rn to Rm, right? Okay? Any n and any m. Now, there's one more case. What's the form of the matrix that represents a transformation from R2 to R3? What's that matrix have to look like? Just go ahead and slop one down with some asterisks. A matrix that would map a vector in R2 to a vector in R3. Yep. So that matrix won't give you a vector in R3.
I'm gonna be honest with you, I had no idea until about a quarter of a second before I started scribbling.
Okay, well, let's reason it out. The matrix multiplies vector this form. So, what was I going to say? It started with R. Rows. Must have length 2, right? Okay. Product is in R3. So what they conclude from the fact that the product is in R3. How can the product be in R3? Well, what we're saying is that you've got a matrix here that multiplies these and gives us one of these, right? Now the matrix isn't going to give us one of these. Got to have 3 rows to get a vector in R3. So it's got to look like this. Okay? Now how can that matrix reduce? There are at least 2 ways it can reduce. and maybe there are more. If you can show me two, I'll be happy. I guess that thing's a 0. Pretty sure it was. Have an extra loop in it. Well, again, why don't you give me examples and prove everything I'm saying? I won't expect it all by next time, but if you get it all by next time, great. If you just have examples by next time, I'll be okay with it, and maybe 1 or 2 attempts at proof, okay? This can reduce to what? Well, it can reduce to 1, 0, 0, 1. And once you've got these, you're going to wipe out whatever's here, right? So this row is going to get wiped out no matter what. Okay? We could also reduce to 1 star 0, 0, 0, 0. Okay? Question, Alden? Are there other possibilities?
So I'll be over the water.
And what does each mean?
I'll see you in the morning.
Yeah, geometrically, right? You got lines, you got planes, you got 3-dimensional spaces. What have you got? What's this transformation doing? Okay? Clearly, you can define this transformation. If you've got a matrix like this, it does define a transformation from R2 to R3. And any transformation from R2 to R3 can be represented by a matrix of this form. So what are the possibilities? Okay?
I'd halfway scribbled something down. I don't know if it'd be possible, but